previous lecture, we defined energy and described the main non-renewable resources. We will now discuss about renewable resources and also discuss the overall scientific and technological challenges of energy. We'll start with biomass. Biomass energy includes charcoal, firewood, agricultural residue, temperate crop waste, tropical crop waste, animal waste, municipal solid waste, and commercial and industrial waste. Biomass energy applications includes biofuels, biopower, and bioproducts. Let's repeat this again. These three energy applications are biofuels, biopower, and bioproducts. Let's go through each of these in further detail, starting with biofuels, which convert biomass into liquid fuels for transportation. Biopower, which involves the direct burning of biomass or the conversion of biomass into gaseous or liquid fuels, which burn more efficiently to generate electricity. And bioproducts, products that result from the conversion of biomass into chemicals for making plastics and other products that typically are made from petroleum. Unlike other renewable energy sources, biomass can be converted directly into liquid fuels called biofuels to help meet transportation fuel needs. The two most common types of biofuels in use today are ethanol and biodiesel. Ethanol is an alcohol, the same as what is found in beer and wine. It is most commonly made by fermenting any biomass high in carbohydrates through a process similar to beer brewing. Biopower, or biomass power, involves the use of biomass to generate electricity. Biopower system technologies include direct firing or direct combustion, co-firing, gasification, pyrolysis, and anaerobic digestion. Most biopower plants use direct-fired systems. They burn bioenergy feedstocks directly to produce steam. This steam drives a turbine, which turns a generator that converts the power into electricity. Co-firing refers to mixing biomass with fossil fuels in conventional power plants. Coal-fired power plants can use co-firing systems to significantly reduce emissions, especially sulfur dioxide emissions. Gasification systems use high temperatures and an oxygen-starved environment to convert biomass into synthesis gas. The synthesis gas can then be chemically converted into other fuels or products, burned in a conventional boiler, or used instead of natural gas in a gas turbine. Using a similar thermal-chemical process, but different conditions will pyrolyze biomass to a liquid rather than gasify it. The pyrolyzed oil can be burned to generate electricity or used as a chemical source for making fuels, plastics, adhesives, and other bioproducts. Anaerobic digestion produces biogas that can be used in standard applications or combined heat and power applications. The petrochemical industry makes a myriad of products from fossil fuels. The plastics, chemicals, and other products are integral to modern life. The same or similar products can, for the most part, be made from biomass. Bioproducts that can be made from sugars include antifreeze, plastics, glues, artificial sweeteners, and gel for toothpaste. We have used biomass energy, or bioenergy, the energy from plants and plant-derived materials, since people began burning wood to cook food and keep warm. Wood is still the largest biomass energy resource today, but other sources of biomass can also be used. These include food crops, grassy and woody plants, residue from agriculture or forestry, oil-rich algae, and the organic components of municipal and industrial waste. Let's talk about the capacity of biomass in the U.S. In 2014, the United States generated about 4,093 billion kilowatts per hour of electricity. About 67% of the electricity generated was from fossil fuels, such as coal, natural gas, and petroleum. The consumption in the U.S. gives us an idea about how effective the different energy sources are growing and are likely to be useful in the coming 25 years or so. The U.S. is one of the few countries where effort and progress are being made in all of the energy resources. Therefore, it provides us with a good idea of the future energy supplies and consumption. By the way, we will use U.S. examples for the other renewables that we discuss later. Notice that the biomass capacities for electricity generation in the U.S. is 1.7%. This is quite small compared to coal, natural gas, and even nuclear. Moreover, it is actually small compared to the overall contribution of renewables to electricity production. Here is a comparison of quantities of coal, oil, and wood for electricity production. Basically, 1 kilogram of firewood will roughly yield 1 kilowatt of electricity per hour. In contrast, 1 kilogram of coal yields 3 kilowatts of electricity per hour, and 1 kilogram of oil yields 4 kilowatts of electricity per hour. Notice that we need a lot of wood and therefore a lot of land space to generate electricity at the level of coal and oil. For example, the land area required for 1,000 megawatts of electricity production by biomass plantations is 4,000 to 6,000 kilometers squared, or the equivalent of a state or small country. In the previous slide, we discussed biomass capacity to produce electricity. Here, we are discussing biomass capabilities to produce oil for transportation. Here is the comparison of average oil yield in liters per hectare for various crops. To put this in perspective, hectare is the equivalent of roughly 5,000 American football fields, or roughly 5,000 soccer fields. Also, remember that a gallon is equal to 3.785 liters. For example, 1 hectare of sunflowers yields 779 liters of oil, or the equivalent of 205 gallons of oil. Let's look at the oil yield of various crops. A hectare of castor can yield 1,413 kilowatts per hour of electricity. A hectare of coconut can yield 2,689 kilowatts per hour of electricity. A hectare of palm can yield 5,950 kilowatts per hour of electricity. Things get more interesting when we consider algae. A hectare of algae gives us 100,000 kilowatts per hour of electricity. This is about 100 megawatts of electricity, which can power about 100,000 homes, about the equivalent of a small town. That is why algae is a strong consideration for yielding oil. However, we must explore methods of growing large amounts of algae. Some pilot plants produce 40 barrels per day. No competition with the food supply. Biowaste and algae grown in wastewater does not need to compete with farmland and food supply. Now let's move to geothermal. The Earth's heat, called geothermal energy, escapes as steam at a hot spring. 99% of the Earth's volume has temperatures greater than 1,000 degrees Celsius. The total heat content is estimated to be 10 to the 31st power joules. The geothermal resource base is sufficiently large. The geothermal resources are generally classified as renewable resources, such as wind, solar, and biomass. Geothermal systems are generally categorized into 1. Steam-dominated systems, 2. Liquid-dominated systems, and 3. Enhanced geothermal systems, or EGS. In the steam-dominated and liquid-dominated systems, steam or hot water is extracted from naturally occurring fractures within the rock and in the subsurface, and a cold fluid is injected into the ground to replenish the depleted fluid. Enhanced geothermal systems consist of impermeable rocks containing hot water. Wells are used to pump cold fluid into the hot rock to gather heat, which is then extracted by pumping the fluid to the surface. When an enhanced geothermal system type reservoir lacks sufficient connectivity through natural fractures, the reservoir is fractured by using high-pressure fluid injection in order to increase permeability and therefore to facilitate fluid movement through rock, just as with the hydraulic fracturing of tight oil and gas reserves. A well is drilled into a geothermal reservoir to provide a steady stream of hot water. The water is brought up through the well, and a mechanical system, piping, a heat exchanger, and controls delivers the heat directly for its intended use. Geothermal hot water can be used for many applications that require heat. Its current uses include heating buildings, drying crops, and heating water at fish farms, and in several industrial processes such as pasteurizing milk. This picture shows the Earth temperature gradient. Notice how hot the solid Earth is. However, there's a limited number of suitable sites. The heat can be depleted if used too rapidly. Here we are showing some of the major geothermal power plants in the world. Notice that geothermal energy are connected to the volcanic region. Also notice that there are still plenty of geothermal energy to be tapped for productions, especially in East Africa and the western region of South America. In these two regions, there are no major geothermal plants, but there is lots of potential. Here we are returning to the U.S. example we mentioned earlier. In 2014, the geothermal capacity in the U.S. for electricity production was 0.4%. Notice how small the amount is, even compared to other renewable amounts. Now let's talk about solar. There are two ways of capturing solar energy, through photovoltaics and concentrating lenses. Solar is generally captured by humans through photovoltaics. The photoelectric effect, that is, the ejection of electrons from a substance by incident electromagnetic radiation, is a process by which a photovoltaic cell converts absorbed sunlight into electricity. Photoelectric was first observed in 1838 and later explained by Albert Einstein. An individual photovoltaic cell typically produces between 1 and 2 watts. The land area required for 1,000 megawatts of electricity production by photovoltaic arrays is 20 to 50 kilometers squared, or the equivalent of a small town. The amount of solar energy that reaches the Earth's surface every hour is greater than the world's total demand for energy in 1 year. Alternative to photovoltaics, one can use lenses or mirrors to capture solar power. That is what solar concentration is about. The concentrating solar power system is made up of lenses, mirrors, and tracking systems, focusing a large amount of sunlight into a smaller beam, The concentrated light heats a working fluid and is then used as the heat source for power generation or energy storage. A concentrated solar power system uses heat to run a motor that creates energy. Solar power can be collected all year round, but more power can be gathered during the summer because of greater amounts of daylight. Areas such as the Sahara Desert, the U.S. states of Nevada and California, and Australia are good places to build a solar power system. However, solar power cannot be controlled by humans because the regional and seasonal effects affect solar power. For example, a solar power station should be located in a well-lit area like the deserts or high ground, where the intensity of the sunlight is highest. Again, we are returning to the U.S. example we mentioned earlier. In 2014, the solar capacity in the U.S. for electricity production was 0.4%. This is quite small, yet one of the best case scenarios in terms of solar energy development in the world. Now we'll be moving to wind. What is wind energy? Wind energy is the movement of air in the atmosphere, which produces wind relative to Earth's surface. Circulation in the atmosphere is caused by pressure differences generated primarily by uneven solar heating. Air flows from areas of higher pressure, where air sinks, to areas of lower pressure, where air rises. So wind is a product of the sun shining on the Earth and the Earth's atmosphere. It is a resource that will not be depleted by tapping it for electricity generation. Wind energy is available for electricity generation in locations where the average wind speeds are great enough to drive wind turbines. Wind turbines start operating at wind speeds of around 15 kilometers an hour and reach maximum power output at around 50 kilometers per hour. At very high wind speeds, or 80 kilometers per hour, wind turbines shut down. Wind plants produce electricity only when the wind blows. So if the wind is not blowing, the plant is not producing electricity. For this reason, wind is called an intermittent resource. The average size of turbines delivered to the market in 2004 was about 1.3 megawatts onshore and 2.1 megawatts offshore. The land area required for 1,000 megawatts of electricity production by wind fields is 50 to 150 kilometers squared, or the equivalent of a small town. This picture shows the map of the U.S. with areas favorable to wind energy production. Notice that the coastal area in red are outstanding areas for wind energy production. There is a growing trend toward offshore wind energy for several reasons. Better wind resources. There's no need for large tracts of land. There's less disturbance to wildlife habitats. It's far away from residential areas, therefore there's less noise. Wind turbine technology converts the kinetic energy in wind to electricity. Village and off-grid applications are important for displacing diesel generation and for improving quality of life, especially in developing countries. Let us again use the U.S. example described earlier to illustrate the wind energy capabilities in terms of electricity generations. In 2014, the wind capacity in the U.S. for electricity production was 4.4%. This is clearly the fastest growing of all renewables, mainly thanks to the offshore wind production. However, this is still small compared to coal and natural gas. This figure shows a chart of the energy consumption in 2013. The major source of energy comes from fossil fuels, and the dominant fossil fuels used today by most industrialized and developing countries are oil, coal, and natural gas. Among these fossil fuels, oil is the most consumed, followed by coal, then natural gas. This figure shows the specific consumption volume for various fuels. Again, we can see that oil, coal, and natural gas dominate the world energy consumption, even in 2013. Ideally, we need an energy resource or a combination of energy resources, which is large enough to fulfill world energy demand in all forms, needed without polluting the atmosphere. Finding this energy resource, or this combination of energy resources, is the challenge of our time, because none of the existing resources, or a combination of resources, can readily fulfill these objectives. That is, enough capacity, transformation to the secondary energy resources, and protection of the environment. Fossil fuels have the capacity to meet the world's energy demand and can be transformed into all forms of secondary energy we need. However, their transformation to secondary energies significantly pollutes the atmosphere. Renewables do not yet have the capacities we need to run modern societies, although they do not pollute the atmosphere. We have a capacity problem as far as renewables are concerned. Renewables remain a very small component of the world's energy portfolio, although recent data suggests that they are starting to hit their stride, as we can see in here. It is clear that fossil and radioactive powered sources are not going away soon. This figure shows global primary energy consumptions by fuel type in 2012 and the projections for 2040. These projections do not suggest any specific significant improvement in renewable output in the next 25 years. Again, let's recall what secondary energy sources are. Secondary energy sources, also referred to as energy carriers, are the more convenient forms of energy that can directly be used by society, such as electrical energy, heating, refined fuels, and synthetic fuels. Electricity is a secondary energy source, which means that we must use primary sources to produce it. Coal, nuclear power, hydroelectric power, natural gas, and oil are the top 5 primary energy sources for producing electricity. Unlike these sources, electricity is not classified as renewable or non-renewable. The fuels for transportation essentially are oil, biomass, and to a lesser extent, natural gas. Electricity comes from coal, geothermal, nuclear, wind, solar, hydroelectric, natural gas, oil, and more. Besides biomass, renewables can produce only electricity, and therefore they do not contribute to powering combustive engines which are based on fuels. The point is that renewables are not only limited in the overall energy capacities they can provide to society, but also in their ability to supply the secondary forms of energy. Climate scientists have observed that carbon dioxide, or CO2 concentrations in the atmosphere have increased from about 280 parts per million in the mid-1800s to almost 400 parts per million in 2013. Significant increases have also occurred in levels of methane, or CH4, and nitrous oxide, or N2O. These increases are causing global warmings and extreme weather events, such as the European heat waves in the summers of 2003 and 2010, which caused massive loss of life. The deaths of at least 130,000 people have been attributed to the heat. Among the many activities that produce greenhouse gases, the use of fossil fuels represents by far the largest source of emissions. Smaller shares correspond to agriculture, producing mainly CH4 and N2O from domestic livestock and rice cultivation. and to industrial processes not related to energy, producing mainly fluorinated gases and N2O. Others here include large-scale biomass burning, post-burn decay, peat decay, waste, and solvent use. Energy emissions, mostly CO2, account for the largest share of global greenhouse gas emissions. CO2 resulting from the oxidation of carbons in fuels during combustion dominates the total greenhouse gas emissions, as seen in this photo. The goal of the IPCC, or Intergovernmental Panel on Climate Change, is to stabilize greenhouse gas concentrations in the atmosphere at a level that will prevent dangerous anthropogenic interference with the climate system. The solutions include a reduction of greenhouse gas emissions by the use of renewables instead of fossil fuels. Renewable energy generally contributes to world energy security, reduces dependence on fossil fuel resources, and provides opportunities for mitigating greenhouse gases. Unfortunately, the limitations of renewables in terms of capacity with respect to world energy demand and in terms of conversion into secondary forms of energy make this solution unrealistic for the foreseeable future. Maybe under a certain number of policies, we can rapidly increase the capacity of renewables, especially for electricity production. Conservation of energy can reduce energy demand, increase environmental quality, and lower energy costs by preventing future resource depletion. We capture CO2 from coal and gas-fired power plants or industrial processes and use boreholes to inject the captured CO2 in the ground. We can convert natural gas to fuels that can be used for transport fuel because natural gas burns much more cleanly than oil. For instance, oil power plants that burn oil emit 50% more carbon dioxide than natural gas plants. However, the conversion of natural gas to fuels is several orders of magnitude more challenging than the conversion of crude oil to transportation fuel. Electricity storage for transportation use, for improving the electricity grid, and even for replacing electricity grids is another scientifically challenging problem. In summary, we have enough energy capacities for decades as far as oil, coal, and natural gas. However, the environmental issues associated with the conversion of these primary resources to secondary resources are major drawbacks. Nuclear energy also has enough energy capacities for decades, but the potential catastrophic effects in the case of an accident on the biosphere are major drawbacks. Renewables have very limited environmental impact, but the capacities are just too small with respect to the world electricity demand and extremely small with respect to world demand of fuels for transportation. Among renewables, only biomass can provide fuels for transportation. To conclude this discussion on energy challenges, let me close with this quote from Jules Verne's. "I believe that water will one day be employed as fuel, that hydrogen and oxygen, which constitute it, used singly or together, will furnish an inexhaustible source of heat and light, of an intensity of which coal is not capable. I believe then that when the deposits of coal are exhausted, we shall heat and warm ourselves with water. Water will be the coal of the future." Thank you for listening to this iMode Education lecture. Remember, there is a large selection of iMode Education lectures which can further enhance your knowledge of energy.